Combining probability distributions, part 1. We're looking at marginal and joint distributions and dependence and independence between probability distributions. To understand this, you'll need to know about fractions and percentages, basic information about probability distributions, and that's about it. So when we think about a probability distribution, we'd normally think about something with quite a number of possibilities in it. In this case, just to keep it simple, we're going to just look at two possible outcomes for each distribution. So if we're looking at the distribution of reasons for studying statistics. We're going to assume that at a particular tertiary institution of people studying statistics, 10% of them wanted to study statistics, 90% of them had to study statistics in order to complete another course, and so that's a valid probability distribution, adds up to 100%. And the idea is, if that's the percentage of people, then if you go and talk to a random person, there's a 10% chance that they'd say, yes, I wanted to study statistics, and a 90% chance that they'd say, I had to study statistics for another course. Now, of course, in the real world, there'd be a lot of other variations in that. We'd have a lot more possibilities than just either they did or they didn't. There might be nuances on that, but to keep it simple, we'll just keep it down to the two. They wanted to study statistics or they didn't. We're going to look at another distribution for the same people, how much they enjoyed mathematics at school. Let's assume that 40% of them enjoyed mathematics and 60% of the people didn't enjoy mathematics at school. And when we put those together, so what we've got now in the margins, not surprisingly, is what we call the marginal distribution. On the right-hand side, we've got the marginal distribution of enjoyment. And on the bottom, we have the marginal distribution of reasons for studying statistics. In the middle, in this grey area, is what we call the joint distribution. If we were writing this as a formula, we'd need to have two different variables for the formula for the joint distribution, because we're looking at situations where two things are true. In the top left-hand column, we're looking at students who enjoyed mathematics and wanted to study statistics. So when two things are true, we're looking at a both and situation, and that means we use the multiplication rule. We're saying that 10% of the 40% of students, or 40% of the 10% of students, either way you get 4% of all of the students both wanted to study wanted to study statistics and enjoyed mathematics at school. In the next column, or the next cell of our matrix there, we've got 36% of students, 90% times 40%, had to study statistics for another course and enjoyed mathematics at school. The multiplication rule sometimes confuses people a little bit because we're thinking about two things having to be true. That's less likely than just any one of them on their own being true. And if we multiply them together, we normally think of multiplication as creating a bigger number. And of course, the probability of two things both being true is going to be smaller. What we need to remember is that probability is represented as a fraction or a percentage of 1, and a fraction between 0 and 1. If you multiply two fractions between 0 and 1, you're going to get a smaller fraction. You're going to get a fraction of a fraction. That's why the multiplication rule gives you a smaller percentage of people where both things are true. In our next cell, we have 10% of the 60%, or 10% times 60% is 6% of students wanted to study statistics and didn't enjoy mathematics, and 54% had to study statistics for another course and didn't enjoy mathematics. So altogether, we still have a valid probability distribution that all adds up to 100%. 4% plus 36% is 40%, plus 6% is 46%, plus 54% makes it 100%. We've covered all the students, and now if we meet a random student, we have the probability that they will fit into one of those categories in terms of their enjoyment of mathematics and having to study statistics for another course. So now, if we have the joint distribution information but don't have the marginal distribution, we can work out the number of people who wanted to study statistics altogether by adding up the people who enjoyed mathematics and wanted to study statistics, plus the people who didn't enjoy mathematics and wanted to study statistics. That's 4% plus 6% is equal to 10%. It's easy to see there. It can be a little bit more confusing when you're looking at formula to realize that to find a marginal distribution, you need to add up the other distributions. So to find the reasons for studying statistics, you need to add up the options of the enjoyment of mathematics and the not enjoyment of mathematics to give you that total, provided all the people you're adding up still want to study statistics. But that's the additional rule at work, rule at work, when either of two things are in place. Either it's the 4% or the 6%, then altogether there's a 10% chance that someone will have wanted to study statistics. Similarly, there's a 90% chance that they had to study statistics. There's a 40% chance that they enjoyed mathematics. And adding 6% and 54%, there's a 60% chance that they didn't enjoy mathematics. Now, all that's fine and it works out very neatly, except that we made an assumption in there that we didn't specify. What we assumed there was that whether you enjoy mathematics and whether you wanted to study statistics are completely independent of one another. And so that's why we could use the same percentages to multiply across and it didn't affect things. So in other words, 4% of people who wanted to study statistics enjoyed mathematics and 6% didn't. That's 4 on 6, that's 2/3. Of those who had to study statistics, 36% did enjoy mathematics, 54% didn't. Again, that's 36 on 54, that's 2/3. That fraction actually hasn't changed. Whether someone wanted to study statistics and whether they had to study statistics, it made no difference in terms of their enjoyment of mathematics. Of course, that's unrealistic. It's unrealistic in the real world very often to find things that are independent like that. Much more likely that whether or not someone enjoyed mathematics at school will have an effect on their desire to study statistics. So let's assume that those percentages are going to change. Let's say that instead of being 4% of all students enjoyed mathematics and wanted to study statistics, let's say that that's now 8%. And let's say that it's 2% of those who wanted to study statistics didn't enjoy mathematics at school. That changes the percentages on the right here. We've now got 44% of students who enjoyed mathematics and 54% didn't enjoy mathematics. It still works when we add up. We're still adding up that left column. 8% plus 2% still gets to 10%. On the top column, 8% plus 36% gets to 44%. So we can still find the marginal distribution by adding up the relevant column of the joint distribution, or the relevant row of the joint distribution. What doesn't work anymore is trying to multiply those percentages out. That breaks down. So 90% times 56% isn't 54%, it's actually 50.4%, and so on. Each of those percentages change. So we can only multiply marginal distributions to get a joint distribution if they're completely independent. And in fact, mathematically, that becomes our definition of whether two distributions are independent from one another. They're independent if and only if you can multiply them together, and that will give you the valid joint distribution. Thank you for watching.